These are the notes for AP Calculus on the topic of interpreting the graph of the velocity function. So the velocity function is a common graph to be given because you can be asked lots of different questions about what is happening based on the graph of the velocity. So in this case, it says Aiden rides his bicycle from his home to Vincent's home, starting at t equals 0 minutes and arriving at Vincent's home at t equals 15. During the time interval 0 to 15, his velocity v of t in miles per minute, those are units, is modeled by the piecewise linear function whose graph is shown below. So this is the velocity function for Aiden on his bicycle. And then part A says, notice here's your time, and this is the actual velocity. Notice it doesn't go by ones, it goes by tenths here. After leaving home, Aiden realizes he dropped his calculus homework, and he returns to get it. At what time or times does Aiden change direction? So remember, what tells you when something changes direction, or what direction something is going, is the velocity function. And that's what we have the graph of here. So the easiest way to figure this out is to draw our number line right underneath the graph. Going to label it v of t. And since this is the graph of the velocity, what we would look at whenever the graph matches your number line, you're just looking at the y values. So you can see the velocity is 0 at the very beginning, at time 0. And then all these y values are positive until we get to 4. So the velocity is positive until 4, we're at 0. Then all the y values are below the t-axis here. So these are all negative y values until 7, where the velocity is 0 again. And then after 7, all of them are above the t-axis. So they're all positive until we get to 15, where it's 0. So notice velocity is positive is when in this case, when he's heading towards Vincent's home, and velocity is negative when he goes back towards his home, the other direction, and then back to positive, again, heading towards Vincent's home. So you can see when he changes direction is when the velocity is changing sign here at time 4 and 7. So we can say at t equals 4, and the units for time here, notice, time is in minutes, and t equals 7 minutes. Aiden changes direction. Or you could say Aiden changes direction at t equals 4 minutes and t equals 7 minutes, either way. And then it says give a reason for your answer, which is just another way of saying justify it. So you could just say since or because. It's because v of t changes sign. You could say at t equals 4 and t equals 7, or you could say at these times. All right, and then for part B, now it says there we go. Sorry, I skipped a page there. It says, find the acceleration if it exists of Aiden on his bicycle at these 3 times, 2, 5, and 12. So remember, acceleration, to go from velocity to acceleration, we take the derivative. Remember, graphically, what the derivative is the slope. So acceleration, we look at the slope of velocity, since we have the graph of it, at these specific times. So let's start with a of 2. Well, at time 2, right here, you can just see it's on this linear segment here. So you could take the coordinates of the points one way. This point is at 3 is the t-coordinate, and 0.2 is the velocity at that time. And then this one's just 0, 0. And find the slope between those. So you can see the difference of the y's here, 0.2 minus 0, divided by the difference of the t's, which is like the x's here, 3 minus 0, gives you 0.2 divided by 3. It's probably easier to work in fractions here than decimals. 0.2 is the same as 2/10. Dividing by 3 is the same as multiplying with the reciprocal, 1/3. And then you can see this reduces. 2 goes into 10 5 times. And then if you multiply across, you get 1 times 1 is just 1 over 15. And then the units, since velocity was miles per minute, this will be miles per minute, which we usually write as miles per minute squared. So that's the acceleration at time 2. Then let's look at time 5. But notice at time 5, we're at a corner. And notice it said, if it does not exist, explain why. So remember, the derivative or slope doesn't exist when you have an abrupt change in it at the corner like that. So for a of 5, you could say a of 5 does not exist, or I could use capital D and E. But it says if it does not exist, explain why, which is just another way of saying justify. Oh, there we indicated the units measure in this one. So we could say since, well, really what's happening, the left and right hand limits of velocity are equal because the graph meets up, but their slopes from the left and right are not equal. That's why we have an abrupt change of corner there. So you'd say since the limit, in this case it's t, it's our t-axis here, as t approaches 5 from the left, but it's not v of t again, the left and right limits of v of t are equal, it's the acceleration a of t. Or I could write v prime of t, and that does not equal the limit as t approaches 5 from the right of, again, a of t. Or you could write v prime of t. Right. So that one didn't exist when you have a corner. Whoops. Sorry about that. And then finally, one more time. Time 12 is right here. And notice on this segment, it's on a horizontal line, and the slope of any horizontal line is 0. So this one's easy. You could say a of 12 equals 0. I guess the units you can put here, but it doesn't really matter since it's 0. But it would be 0 miles per minute squared. So notice on all these, we were trying to find the slope of velocity to get acceleration. Okay. Then part C says at time 4.5, so notice 4.5, that's right there on our graph, is Aiden speeding up. Speeding up is another way of saying speed is increasing. If you're speeding up. Slowing down is another way of saying speed is decreasing. Or neither, that would mean speed is constant if it's not increasing or decreasing. Staying the same. All right, so remember there's two things you need to figure out if the speed is increasing or decreasing, and that's the velocity and acceleration. Because remember, speed is defined as the absolute value of velocity, so speed can never be negative. So let's look at this time 4.5 and figure out both the velocity and acceleration. So the velocity of 4.5, you don't have to get the exact value. We just need to know if it's positive or negative. So v of 4.5, you can see right here, it's you can see even on our number line here, it was negative, velocity was negative here because it's below there, so it's got some negative value there. So that's less than 0, looking at the y values. The y value right there, I should say. And then a of 4.5, again, you could get it exactly, but you don't have to. You just have to see if it's positive or negative. In this case, notice the slope here, it's on a negative. This has a negative slope, so you could calculate it, but we can just tell it's also net less than 0 because by looking at the slope, it has a negative slope there. So it's speed increasing or decreasing. Remember, you have to compare the signs. If they're the same sign, both positive, both negative, that means speed's increasing. They're working together. If they're opposite signs, speed is decreasing. They're going against each other. In this case, they're both less than 0, both negative, so that means speed is increasing. So we can say at t equals 4.5, Aiden, you could say Aiden's speed is increasing, or let's word it the way they did. So you could say Aiden is speeding up. And then your justification would be since, because it says justify your answer, all you'd have to say is since v of 4.5 turned out to be less than 0, and a of 4.5 turned out to be also negative, less than 0. Or you could also word it, you could say since v of 4.5 and a of 4.5 are the same sign, that would work too. All right, now let's take a look at part D. Now we've got another character in our problem here. It says Brandon starts riding his skateboard from his home to Vincent's home at t equals 0, started at the same time, but arrives at time 16, so 1 minute later. During the time of 0 to 16, his velocity, this is a capital V of t. And in mathematics, the capital and lowercase mean different things. So this is a different function. But this time we're given his actual equation instead of given the graph. This is Brandon's velocity. And it says, who traveled farther? Aiden or Brandon, and by how much? Show the work that leads to your answer. So traveled farther is another way of saying what's the distance they traveled. So I'll write the formula right here, first of all. I've got a little more room right here. Next to graph here. So the total distance traveled on some interval from A to B, okay, equals, and here distance, remember, can never be negative. You never say the distance between two things is negative. It's always something either positive or 0. So to go from velocity to back to distance, which is kind of like position, you'd have to integrate, in this case from A to B. But to make sure it's distance, it's never negative, we wouldn't integrate velocity by itself. We'd integrate speed, which is defined as the absolute value of velocity. Because speed, like distance, is also never negative. So that's the formula we're going to use for both Brandon and Aiden. The difference is for Aiden, we have the graph of velocity, and for Brandon, we have the equation for velocity. So we're going to find the same information in two different ways here. So let's say we start with Aiden. Okay, so for Aiden, notice his, the distance he traveled, he went from 0 to 15. So that's the interval. So it'd be the integral from 0 to 15. Oops. And then it'd be the absolute value of v of t dt. No, this is the lowercase v of t, not uppercase, because that was what the graph was called. So you just have to remember the definite integral graphically represents the area between the graph and the x-axis, or in this case, the t-axis. So we have to find these areas. However, the absolute value is going to turn any negative ones to positive. So let's start with this triangle right here. You can see for this one, it's 1/2. The base is 4 times the height is 0.2. So 4 times 1/2 is 2 times 0.2 gives you 0.4. So that's the area of that one. Then let's take a look at this triangle right here. So for this triangle, it's 1/2. The base is 3, and the height is 0.2. So here's probably easiest to do half of 0.2 instead of half of 3. Half of 0.2 is 0.1. 0.1 times 3 is 0.3, but it's below the x-axis, so it's negative 0.3. Okay. It's negative because he's going back towards his house, but since we want distance traveled, that's where the absolute value comes into play and changes this negative to positive. Because you can see up until 7 seconds, if you want the distance he actually traveled, he traveled 0.4 miles away from his home and then 0.3 miles back towards his home. So the distance he traveled is actually 0.7 at this point. And then this one you can split into 2 triangles and a rectangle, or you can just do it as one big trapezoid, which is what I'm going to do. So remember, for the area of a trapezoid, it's 1/2. The width here, from here to here, between the parallel lines, is 3. And then the heights are the lengths of the parallel lines. So this one is a length of 3, plus this one from 7 to 15 is 8. So here, if you add those up here, 1/2 of 0 of, oh sorry, it's not 3, it's 0.3. Half of 0.3, half of 3 would be 15, half of 0.3. So I'll probably just write that again so it's a little clearer. 1/2 times 0.3 is 0.15, and then times 11. Well, you can first just go 11 times 15 is 165, and then move the decimal 2 places. So this one is 1.65, and it's above the t-axis here, so it's positive. And then you add those all up, and we get, this is 0.7 plus 0.65 gives you 2.35. And the units for distance here are miles. So that's how far Aiden traveled. Now, for Brandon, instead of the graph, we're given the equation. So notice for Brandon, it says his interval was from 0 to 16. He arrived at time 16, so instead of 0 to 15, it'd be 0 to 16. And then we just would have to integrate this. Absolute value of 1/20 square root of t dt. And then you can see, does the absolute value ever affect this? Well, we're plugging in numbers from 0 to 16. See how it's in the square root there? That's never going to be negative. So in this case, the absolute value doesn't do anything. So this one will integrate by hand. You can pull the 1/20 out in front as a constant. Then we've got 0 to 16. And then you can rewrite this so it's easier to integrate as t to the 1/2. Again, the absolute values don't have any effect here, dt. And if we move it up here, we've got 1 over 20. And then when you integrate t to the 1/2, you get t to the 3/2. Instead of dividing by 3/2 times 2/3. And that's divided from 0 to 16. And then you can pull out the 2/3. You can see the 2 goes into the 20 10 times. So then we have 1 over 30 on the outside. And then if we switch that back to radical form, it'll be a little easier to evaluate. So instead of t to the 3/2, it's the same as the square root of t cubed. So we've got 1 over 30. If you plug in 16, square root of 16 is 4. 4 cubed is 64. Minus when you plug in 0, it's just 0. So for Brandon, we got that he traveled 64 over 30. You can divide those both by 2, gives you 32 15ths, which, if you make it a mixed number, is a little easier to compare. Would be 15 goes in 32 twice, and there's 2 15ths left. What else? So you can probably tell which one's bigger right now. 0.35 is bigger than 2 15ths. Okay, because this one's a little bigger than a third, which would be 0.333 forever, and 2 15ths is less than a third, because a third would be 5 15ths. All right, so we can see that Aiden actually traveled farther, but it also says by how much. So to get that part, we just have to subtract these two. So when you subtract them, the 2's cancel out. That's easy. So let's just make a deal with the fractional part. So what we'll have left is 35 hundredths minus 2 15ths. And then you can get a common number right now. Oops. Or if we reduce this one first, it might be a little easier. 35 hundredths, you can divide these by 5, reduces to 7 over 20. You divide those both by 5. And now it's a little easier to get a common number for 20 and 15. Notice those both go into 60. So if you multiply this one by 3, you get 21 over 60. Minus, if you multiply this one by 4 to make it 60, you get 8 over 60. Subtract those gives you 13 over 60 miles. So that's the difference between them. That's how much farther Aiden traveled. So we just have to write our answer here. Aiden traveled 13 over 60 miles farther than Brandon. All right, now let's take a look at a similar question. It says, who lives farther from Vincent's home, Aiden or Brandon? So it sounds like almost the same question, by how much, but this one doesn't necessarily mean the same thing as distance traveled. Who lives farther, that's another way of saying the change in position. Or another word for that, it's also called displacement. Basically, how far are they from where they started? And then on some interval from A to B. Again, since it's position, to go from velocity to position, you have to integrate velocity. So this one equals the exact same thing, the integral from A to B, but displacement or change of position, you have to account for a velocity being negative, because that means over here, Vincent's going back towards, Aiden's going back towards Vincent's house. So you still integrate from A to B, but now you only integrate velocity, not speed. because displacement, the change of position could be negative. You have to account for that. So we've actually done a lot of the work for this already. We already found these areas. So let's start with Aiden again. So for Aiden, again, it's going to be the integral from 0 to 15. The difference is it's not going to have the opposite value signs. It's just going to be just velocity, v of t. So it still represents the areas. Sorry, that's not a very clear dt there. But now, since there's no absolute value, we're not going to change this negative one to positive. We're going to leave it negative. Because notice after 4 seconds, he's gone 0.4 miles, but then he backtracks 0.3. So Aiden's displacement after 7 seconds is actually only 0.1 miles away from his home. That's his change of position, versus he actually traveled 0.7 because he backtracked 0.3 miles. And then we get plus 1.65 still. That was still positive. So that's 0.1 plus 1.65. That gives you 1.75 miles. So that's actually how far, based on the scenario, he lives away from Vincent's home. He just had to travel farther than that because he backtracked 0.3 miles. So that actually added an extra 0.6. You can see this is 0.6 less than the 0.235. But then for Brandon, this one's even easier because remember the absolute value didn't affect his at all. So the integral from 0 to 15 of his velocity, which was capital V of t 1 over 20 square root of t dt. And since the absolute value had no effect, Brandon's going to be exactly the same, 2 and 215. So we already integrated that. We don't have to do that again. So in this case, that's actually bigger than 1.75. So to figure out by how much, Brandon actually lives farther away from Vincent's home, even though he traveled less because he didn't backtrack. So if you make it a single fraction, it's probably a little easier. 15 times 2 is 30 plus 2, so that's the same as 32 thirtieths, minus 1.75, that's 1 3/4. So that's the 4 times 1 is 4, plus 3 gives you 7/3, 7/4. Okay, so again, here the common denominator, you could reduce some of the common number is still going to be 60. So if we multiply this one by 2, that'd be 64 over 60. If you multiply this one by 15, no, it's not 64. Let's see. Oh, sorry, 32 over 30. Why I did it? Sorry about that. I don't know why I made it over 30. It should be over 15. My bad. So that one doesn't reduce. 32 over 15. So the common number is still 60, but now it's not 64 over 60. We have to multiply it by 4, so I give you 128 over 60. Minus, then multiply this one by 15, would give you 105 over 60. So when you subtract those, you actually get 23 over 60 miles. So that's actually how much further, based on the scenario, Brandon lives away from Vincent's home than Aiden. Okay? So we can say Brandon lives 23/60th miles farther from Vincent's home than Aiden. All right, one last thing here. Here it asks us to write expressions for Aiden's acceleration, velocity, and distance from his home that are valid from the interval 13 to 15. So notice it's not for the whole function, just for this section right here. We want the acceleration, velocity, and position functions. So the easiest one to start with is actually acceleration, because the acceleration is just the slope. Notice this point is 13, 0.3, and this point is 15, 0. So if we just find the slope between those, we'll get acceleration. So it's acceleration a of t on that interval. It's going to be that slope. So if we take the difference of the y's, 0.3 minus 0, over the difference of the x's, what's 13 minus 15? Gives you 0.3 over negative 2, which again, if you just write it as a fraction, it's easier. So 0.3 is 3/10. Divided by negative 2 is the same as multiplying by the reciprocal, 1 over negative 2. So we get negative 3 over 20. So that's what a of t is on that interval. That's an easy one to start with. Then to give velocity, to go from acceleration to velocity, you have to integrate. Because to go from velocity to acceleration, you take the derivative. So now we're going to integrate acceleration. So v of t is going to equal the integral of a of t, which was negative 3 over 20. And then we've got dt. And it's an indefinite one because we want the actual equation. Just like it's just acceleration happened to be a constant. Okay, so v of t, would be when you integrate a constant, you just get times the variable, so it'll be negative 3 over 20 t, and then an indefinite integral plus c. But since we're going to have another constant later on the problem, I'm going to call it c sub 1. All right, then you can plug in some point on velocity to solve for that constant. And you can use any point on the interval here. We could use 13, 0.3, but it's probably a little easier to use this point, 15, 0. So we're going to plug in 0 for the velocity and 15 for the time to solve for c sub 1. And then notice that reduces nicely. You can divide both these by 5, gives you 3 and 4. So you get negative 9/4 plus c, and then just add a 9/4, so we get c equals 9/4. So now we can write our velocity function now that we know what that is. Put it right in there. And now we know v of t on that interval, this velocity function, is negative 3 over 20t plus 9/4. And then finally, the last one we need is position or distance from his home. That's another thing. So x of t, to go from velocity to position, you have to integrate velocity. Now we know what the velocity is. So here we're going to have to integrate negative 3 over 20t plus 9/4. Okay, so x of t would equal, when you integrate this, negative 3 over 20 stays out in front. And then integrate t, which is t to the first, you get t squared over 2, plus, when you integrate a constant, 9/4 t. Okay, and then we need to plug in a point on position. So, you look carefully, we actually found one on that interval already. Notice right here we found his actual position, Aiden, at time 15 is 1.75 or 7/4. So that's the point I'm going to use here to plug in to find position. So we know his position is 7/4 at time 15. So I'll just simplify this to be -3/40. And then we'll have 15 squared plus 9/4 times 15. All right, so we just have to, oops, I forgot the plus c sub 2. So we're plugging that in, sorry, to solve for that other unknown constant. So we've got 7/4. And then here you can reduce that a little bit. So this is 15 times 15. But the 40 and 15, you can divide those by 5. So that'll give you 8 and make one of those 3. So now we just have 3 times 3 is 9 times 15 gives you 9 times 10 is 90, 9 times 5 is 45. So 90 and 45 gives you 135. All that's left on the number is 8. And then here, this one doesn't reduce, so just 9 times 15. Again, we already got that. It'd be 9d plus 45 is 135 again, but this time it's over 4 plus c sub 2. So you can get common denominators here if you want. That's one way to handle it. Or in this case, if you just want to solve this and wipe out the fractions, notice the common denominator for these is 8, so you might want to just multiply the whole equation by 8. Because 8 divided by 4 is 2. 2 times 7, that's 14. Here the 8's cancel, so you get -135. Again, 8 divided by 4 is 2 times 135 is 270. And then just don't forget to multiply the c sub 2 by 8 also, so plus 8 c sub 2. And then you can combine those. You get 14 equals 270 minus 135 is 135 plus 8 c sub 2. Subtract the 135, gives you negative 121 equals 8 c sub 2. Divide by 8, so you get c sub 2 is -121 over 8. And then you can just plug that right back in here. And we'll have our position function is x of t equals, this is -3/40 t squared plus 9/4 t. And we just figured out c is -121 over 8. So there's our position function on that interval. And that concludes the notes for AP Calculus on the topic of interpreting the graph of the velocity function.